Hello, discrete math fans. What we're going to do now is give a way to relate the quotient remainder theorem to floor and ceiling. And what we'll do is we'll come up with a formula for how to compute the quotient and the remainder using floor. All right, so the theorem says that if n is an integer and d is a natural number, then if we choose q to be the floor of n over d and r to be equal to n minus d times the floor of n over d, then we can prove that n is equal to dq plus r, and 0 is less than or equal to r is less than d. And if you'll remember, these two things here are exactly what we get out of the quotient remainder theorem. So what this theorem is giving us is an explicit way of computing the q and the r that show up in the quotient remainder theorem. I mentioned this earlier in a more roundabout way by talking about how you would actually use a calculator, a wimpy calculator, to compute the quotient and the remainder. Now we're formalizing this. All right, so we note that the conclusion of this theorem is just telling us that q and r comes from the quotient remainder theorem. All right, so let's prove this. We'll choose q to be as stated in the theorem. Q is the floor of n over d. R is equal to n minus d times the floor of n over d. Now if we calculate what dq plus r is, well, remember that q was the floor of n over d. So here's dq, and here's r. You can see what it all adds up to is just n. So that proves the first part of the theorem, that n is equal to dq plus r. Now we want to prove that 0 is less than or equal to r is less than d. Now remember that q is equal to the floor of n over d. And what does that mean? Well, by the definition of the floor function, it means that q is less than or equal to n over d, and that's less than q plus 1. That's just the definition of floor. Whatever integer you get out has to be smaller than n over d, at least less than or equal to, but the n over d has to be strictly less than the next integer up, q plus 1. All right, let's multiply everything by d. We'll get dq is less than or equal to n is less than d times q plus 1. We'll subtract dq from both sides. Now we get 0 is less than or equal to n minus dq is less than d. Remember, what was r? R was n minus dq, so we've proven it now. We've proven that r is between 0 and d, not including d. Okay, that's all for now.